coming in from Michigan, where I hear that the university was closed down yesterday, so please trust me when I say that I'm very happy to be here. So today I'll tell you about some things we've been thinking over at Michigan. This is work done with James Wells and a graduate student, Sam Rowland. This is something that we hope will turn into a series of papers. The first basic idea we already put out in this paper that came out just a little over a month ago, and hopefully there'll be more to follow soon. So it was pointed out to me last week that Archive has switched to a 5-digit identifier, so this soon doesn't work, so I should switch to a 5-letter word. I haven't been able to think of anything better than never, so we'll see how that goes.
Someday.
Anyways, so let's start with the big question that we all stay up at night and wonder about, right? So where's new physics? And in this talk, when I say new physics, I will take it to mean supersymmetry. Of course, it could be some other kind of physics, but what I have in mind is some kind of supersymmetric theory, because that's what most of us in the field have been working on for all these years, right? So what is the scale of new physics? What is the scale of supersymmetry? So if you go back to the guidebook and think about what guides us in our search of supersymmetry, it has been driven by a few very astute observations. The first one is, of course, the hierarchy problem, right? And it says that you have all these dangerous loop corrections coming from the top loop, and you want to cancel them before it gets too bad. In other words, you want to cancel them with some top partner at something close to the weak scale. And so that gives us a pointer that there should be some kind of new thing that should show up around the weak scale. And so that's driven our thoughts for a long time. Something else has been driving our thoughts for a long time, and that goes by the name of the WIMP miracle. Right? So that says that there is dark matter, and it just so happens that if there's a weak scale particle that interacts through weak force-like interactions, then it freezes out from the thermal bath with just the right abundance to be the dark matter abundance that we see in the universe today. And that really works in supersymmetry, because if you stabilize the lightest neutrino through R parity, if its mass is a few hundred GeV to a TeV, we know that it can give you the right dark matter density. So these have been our key ideas, right? So the hierarchy problem and the WIMP miracle, we've been hearing about these for a long, long time, and they seem to point to a very natural scale for supersymmetry, which is close to the weak scale. And so this has been our working assumption for all these years. This picture, of course, comes with a very strong set of predictions, right? And so it predicts a lot of things about a lot of different particles. First of all, it tells us that the Higgs should be not too heavier than the Z boson. It might possibly have some structure that distinguishes it from the standard model like Higgs, because in supersymmetry there are two Higgses, the up type and the down type. They mix in some non-trivial fashion, and so maybe you can see some deviation away from a standard model like Higgs. But that's a minor thing. The main thing is that it should really be close to the Z mass, because you equate the coupling, the quartic with the gauge couplings in SUSY, and that tells you that the weak scale is where you want to see the Higgs boson. It also tells you that the stops need to be light and the gluino needs to be light, because if you want to cancel the top loop, that's where these corrections need to come in. So naturally, they should be close to the weak scale. So close to the weak scale that we should have seen them at the LHC in the first run. It also tells you something about dark matter, right? So it tells you that if it's indeed some kind of supersymmetric particle, then all these direct detection experiments that have been running over the past few years would have been expected to probe the parameter space of the lightest neutrino. So it comes with this set of predictions. And of course, we all know how these predictions panned out. Right? So the first one told us that the Higgs mass needed to be close to the Z mass. It came in at around 125 GeV, which is not exactly the Z mass. So in terms of the traditional tuning that people talk about, this is about a percent level tuning in parameters to make this number come out properly. And nothing that distinguishes it from the standard model like Higgs so far. Right? So that one didn't turn out to be the most desired number. We've all seen these plots many, many times now, right? So the LHC did not find any signs of supersymmetry. Bounds on superpartner masses are now close to a TeV scale. So for the stops and gluinos, they are close to a TeV unless you go to very squeezed spectra or something non-trivial like that. And that, again, points to a percent level tuning of parameters in your supersymmetric model. Prediction number 3, dark matter, right? We haven't seen anything yet, and that's why we plot these exclusion contours instead of actually looking at signal regions. There are some hints of signals at lower masses, but then we don't really expect SUSY to be active there. So generally, this is the parameter space for SUSY, and we have not seen anything there. And if you think about what that involves, that turns out to involve some kind of fine-tuning in the parameters to land you with a cross-section that's fairly low. Right? So this is a plot that I made as part of my PhD, and this tells you that if you want to go down in direct detection cross-section, you have to go up in fine-tuning in the electroweak symmetry breaking sector. And so this involves some non-trivial tuning. And if you look at where the limit is now, so around 100 GeV, it's around 10 to the minus 45. And that tells you that for a 100 GeV particle, that's a tuning of a few percent, right? So that's what it is.
This tuning is what is the origin of this tuning?
This is the same source as the electroweak symmetry breaking thing. So the mu parameter as compared to the Higgs
Why do you
band.
have to tune the mu parameter to account for the dark matter abundance?
So generally, you're playing with BNOs, VNOs, and Higgs-NOs. Okay.
So this tuning is not somehow the tuning to get the Higgs to be right. For this tuning, you don't care about the Higgs. You're just trying to reproduce the dark matter relic density?
So you don't even care about the dark matter relic density in this plot. So if you just assume that the relic density is what it is, and what is the cross section
in the
comes out to
MSSM,
be
and this is the tuning
in the MSSM.
to get the Higgs.
This is
What's the origin of this tuning?
the origin of this tuning is basically, so the tuning measure is basically just the mu parameter over mz. It's the traditional. Your mz goes as uptype Higgs mass
You are
minus
imposing,
mu squared.
this is in the MSSM, and you're imposing the right value of the Higgs. What are you imposing?
You are just making sure that the z mass comes out right. So it's the usual mz squared is image up squared.
Just the Z mass and the relic abundance.
Not even the relic abundance, just the z mass.
So you're saying that
It's-
the mu parameter has to be much larger than mz when the tuning is...
Yeah, so to have this cross section to go down, the mu parameter has to be much larger than mz, and that's basically the tuning. So it basically just goes as mu squared over mz squared, and that's coming from the fact that if you have a well-tempered neutrino, then you have a large direct detection cross section. So you want to decouple the Higgs-NOs, and so that's basically the source of this tuning.
So just to rephrase it again,
Mhm.
if mu were quarter mz,
Right.
what you're saying is that the Higgs-NO is basically the Higgs-NO dark matter, right?
Yes, if you have a mu close to an mz, so either you have a mixed Higgs-NO, gauge-NO dark matter, in which case you would get a really large direct detection signal, or you would have a pure Higgs-NO dark matter,
or
and
too
then-
much annihilation. I mean,
and then
if
you have
mu-
too much
if mu is
annihilation,
too
and
small,
then your relic density goes
then
up.
the relic density
Indeed.
wouldn't be right. So there must be some relic density constraint in this.
Yeah, so
too.
for a pure Higgs-NO candidate, the relic density plays a role. Otherwise, if it's, as soon as it's less than 80% Higgs-NO, the relic density doesn't come in. But for a pure Higgs-NO, you need that caveat. Yeah.
Mhm.
Yeah, so you could think of a non-thermal scenario where light Higgs-NOs come out with the right relic abundance, and then that would take you away from this pattern.
Yeah, okay.
Yeah. Right. So, so all our ideas seem to have not met with much success, right? And so maybe it's time to think away from this traditional line of thinking about SUSY. So maybe you start to wonder that naturalness is not a good guiding principle. The Higgs mass might be a number that comes out fine-tuned, right? So there might be some kind of fine-tuning in nature that gives you a light Higgs and a light electroweak scale. But then everything else in the supersymmetric sector might be sitting up at some high energy. And so this is what people who work with split SUSY or high-scale SUSY, this is the path that they take. So everything else is at some high scale. The Higgs just happens to be at the electroweak scale because of some tuning in nature that we can't explain. And if you take that point of view, dark matter might not be a WIMP either, right? So if you want everything at a high scale, everything in your supersymmetric sector sitting at a high scale, then there's no natural sort of dark matter candidate. If you go into some kind of split spectrum, then you can expect your Higgsino and Winos to be around the TeV scale and give you dark matter, but maybe the WIMP paradigm doesn't work out either, and maybe dark matter is not your traditional neutrino WIMP. So if you think about this line of thinking, where does that take us? Right? So it takes us back to our question, what is the scale of new physics? And now we don't really have a good answer for where supersymmetry might lie. So the only positive information that we've gained so far in all this discussion is that now there is a measurement of the Higgs mass, right? So that is a solid number that we can reproduce in our theory and think about what that means. So what does that mean? In the MSSM, if you look at the scale of fermion masses that are needed to give you the right number, then this is what it means, right? So as a function of tan beta, of course, if tan beta is large, then you need a smaller correction from stop loops, and then your stops can be about, I think, 5 TeV is the largest you can go without mixing. And then as you crank down on tan beta, as you go closer to order 1, they go up further, closer towards the PeV scale and even further up. So this is going to be my region of interest for this talk. So if you have an order 1 tan beta in the MSSM, your SUSY scale is going to be close to 100 PeV, for example. Right? And so the Higgs mass together with tan beta order 1 seems to tell you that supersymmetry lives at around that scale. So hundreds of PeV scale instead of the TeV scale that we would like to think of it. So where do you go with that number? So we had these two things to guide our thinking, right? And so we've sort of abandoned both of them. Instead of the hierarchy problem, we just have a Higgs mass that we want to reproduce. And instead of the WIMP miracle, we just know that there's dark matter with some relative abundance, and we would like to match that in our theory somehow. So other than these, what else can you use? There's something else beyond the standard model that points towards physics beyond the standard model, right? And we never use neutrino masses as a guide to thinking about SUSY, but then this is something that is solid evidence for physics beyond the standard model, and it would be nice to somehow tie this to some supersymmetric sector. Right? So that is going to be our plan. Of course, there's also the baryon asymmetry. I won't talk about it, but it's something that also needs physics beyond the standard model, and it'll feature indirectly, but I won't have much to say about that. And there's inflation, of course. Okay, so neutrino masses. We all know that in the standard model they're massless. The fact that we see oscillations mean that there's some small mass scale for the neutrinos. We don't know what that mass scale is exactly. We know what the mass differences are, and we know that they have to be fairly light. There's some upper bound that says that they have to be sub-eV. So we know some things about neutrino masses, not all of them. Right? But then we really know that we have these numbers that need to come out of our theory eventually. The way we get neutrino masses, so this is not going to be the Higgs mechanism, right? So the way neutrino masses are realized in most people's minds are that you do some kind of seesaw mechanism that gives you the neutrino masses. The way it works is that you add 2 or 3 right-handed neutrinos to your sector, and then so N1s, you add this Dirac mass term that you're allowed to write down that couples these right-handed guys to the Higgs and the left-handed neutrinos. You have a Majorana mass for these right-handed guys because they're not charged under any symmetry, so you can write down a Majorana mass, right? And so if this mass scale is much bigger than the Higgs Webb scale, then the neutrino masses come out to be roughly the Dirac mass squared over the Majorana mass, which gives roughly that, and that seems to give you active neutrino masses if Y and M are appropriately chosen. Right? So this is the picture that we've known so far. And if you want Y to be order 1, then M turns out to be around 10 to the 14 GeV. So we imagine that this is some kind of gut scale seesaw mechanism taking place in nature. But of course, they don't have to be order 1 and 10 to the 14 GeV, right? So anything that maintains this ratio is allowed. So really, there's no direct constraint on what Y is and what M is.
What is the dimensionality of Y? Is Lagrangian here?
It's dimensionless, right?
So something wrong with MA equals Y squared over M.
There's a Higgs above.
So yeah, so the Higgs web is a dimensional.
Oh, that's,
right?
okay.
So that's
Oh,
mass.
sorry,
Yeah.
I was reading that as a function. Never mind.
Right.
Never-
All right. So that's actually a number that goes
Not
in.
awake yet.
Yeah. Right. So that's one choice of parameters, but then there are several others that can give you the same thing. So there's really no direct pointers to what that scale is. People have thought about this, and there are some numbers that they would like these numbers to be. Right. So it's known that if one of these right-handed neutrinos were at a keV scale, turns out that you can very easily make it into a pretty good dark matter candidate. So it's fairly easy to come up with an approximately correct Rayleigh density. So that's a desirable number for that mass scale to be. In addition, people have found that if there are two sterile neutrinos that are sort of order GeV scale with a very small mass splitting, you can use that to get baryogenesis. So the keV to GeV scale is maybe a good target for where you want your sterile neutrinos to be, because then they can do all of these for you.
So if I can't remember, the KeV, is that warm dark matter, or when does warm dark?
Depending on how you produce it, it's going to be warm or not. But yeah, if you just produce the most straightforward way, it's warm. And I'll have more things to say about that. And so this setup has been fairly extensively studied. It goes by the name of the Neutrino Minimal Standard Model, or the new MSM. Right? And so all it does is it takes the standard model fermion content, it adds to the 3 active neutrinos, 3 sterile neutrinos, right-handed guys. The lightest one is around keV, 10 keV scale, and that gives you dark matter. The heavier two are around the GeV scale with a tiny splitting, that gives you baryogenesis. And so this is a setup that's been very extensively studied. It's been around since 2005, so 10 years now. And so it claims to solve all these problems that we see, and so it's been very extensively studied. If you're nitpicking, then there are 2 issues that might make you uncomfortable with the setup. Right? So one issue is that if you want the active neutrino masses to come out right, then this coupling that I showed you earlier here needs to be around 10 to the minus 7. So of course we want our couplings to be either 0 or 1. If they're not, then we need some kind of explanation for why they're so small. And so that's something that you would like to be explained in this setup. The other issue is that it is not so straightforward for your keV guy to be all of dark matter. And so these are 2 things that you might hope to improve with a more complete theory.
You say just very briefly, why is that? What's the problem?
Oh, this one?
Yeah.
I will get to it in a few slides, but
No, just
you need some
all
non-trivial
of it.
mechanism to produce them. But I'll get into that. So here is our idea of how you can maybe try to fix things. So let's see. So remember that you needed these terms to get the usual seesaw mechanism to work. And this assumes, of course, that the right-handed neutrinos are singlets under all symmetries. Right? That's why you can write down this mass term. It might well be that they are not singlets under all symmetries of nature. So maybe they're charged under some symmetry that we don't know yet. To be more specific, let me call it a U1 prime, but it could really be any other symmetry. Right? So if they're charged under some symmetry of nature, of course, you cannot write down things like that. So this is not allowed, this is not allowed, and so your traditional seesaw mechanism straight away doesn't work without any other modifications. What you can do, of course, the next step is to make U1 prime singlets out of your sterile neutrinos, right? So to couple, so if you pick a new field, call it phi, that is charged under this U1 prime such that a phi n is a singlet under U1 prime, then you are allowed to write down this term, right? So anywhere an n phi shows up is a U1 prime singlet, so that's fine. So this is the lowest dimension operators that you can write down in your superpotential. So I'll talk about superpotentials because we'll imagine that this is a supersymmetric theory, and so this is the first 2 terms that you write down. if the singlet now, so if the scalar component of this field gets a VEV, then you are back to something that looks like a Majorana mass for these right-handed guys and a Dirac mass that talks to the Higgs and the left-handed guy. Right? So you would end up with a mass matrix that looks like that. So this entry is, so imagine this is a 3x3 for the active neutrinos, the lower 3x3 is for the sterile guys, and so they get a Majorana mass term that goes as 5f squared over m star, and so m star is some high energy cutoff that you now need because these are all higher dimensional operators that need to be suppressed by some mass scale where you imagine that they will be UV completed. Right? So this might be the Planck scale or the Gutt scale or some scale of even higher new physics. So that's the mass scale you get, right? And then you're back to doing a seesaw again, and the seesaw tells you now that your sterile guys will be at a mass that's phi squared over m star. The active guys are now Dirac mass squared over Majorana mass again, which gives you, again, the Higgs VEV squared over m star. And once you fix these numbers, you also fix the mixing between the active and the sterile sectors. You get a relation between these numbers, right? And so if you want an idea of what the numbers need to come out to be, this is what they need to come out to be. So this is the x-axis is the active mass scale, the y-axis is the sterile neutrino mass scale, right? So let's see, so 0.05 eV is where you roughly want to be for your active neutrinos. So you can see that if you want your sterile neutrino guys to be from a keV to a GeV scale, then you're talking about a 5eV. So these are contours of 5eV times this coupling. And so you're talking about a 5eV of order of PeV to 100 PeV. And this is sort of nice because this is what the Higgs mass tells us that the supersymmetric sector needs to be at if you realize the mass with an order 1 tan beta.
So the mixing angles, though, as you go up the KV scale, the mixing angles become extremely small.
Sure. Yeah. So as you go up in mass, your mixing gets suppressed. Sure. So there's that. Yeah. And that'll have very interesting observation.
So I just want to point out that I don't think this KV neutrino is related to the experimental claims of sterile neutrinos at all. Right? Those are around 1 eV or something.
You mean the oscillation
Yeah.
data? Yeah. So those are, yeah. So this is purely motivated from trying to get a dark matter component out. Yeah. So the mixing angles would be very small.
This is a simple, just to make sure I understand what's going into this. This is a simplified 2x2 thing, right?
Yeah.
Because really,
Yeah, so I've
you
taken
have-
all the structure
you
out
have
of the
this enormous
matrices.
hierarchy within this sterile neutrino sector, right? Like
Mhm.
6 orders of magnitude.
Yeah.
So,
Yeah. Right. Yeah. Indeed. Anyway, so at first look, right, this turns out to work out fairly nicely. So you get sort of the active and sterile masses you want by putting in a scalar VEV that's around a PeV to 100 PeV, and the X and Y couplings are going to be mostly order 1. Right? So that seems like an attractive scenario to look at more carefully. So another issue I mentioned, right, remember that if you have I-scale SUSY theory, then you don't have a natural dark matter candidate because your Higginos and Winos are now all sitting up at some PeV scale, and so they don't give you the right radic density. So you need something else to make up dark matter. And sterile neutrinos are known to be a potential dark matter candidate, so let's see how this story pans out. So the first thing, of course, is that they don't follow the usual thermal freeze-out story because they're so weakly coupled to everything else that they're never in equilibrium. Right? So they're produced some other way. The way they're produced is that there is some mixing between the active and sterile neutrinos just by virtue of diagonalizing your 6x6 matrix, mass matrix. And because of that mixing, any reaction that produces active neutrinos will also, through this mixing, produce some sterile neutrinos. And so you expect your processes in the early universe to produce some sterile neutrinos as well. And they accumulate and can contribute to dark matter. And so people have done this calculation many, many times. The dark matter abundance that comes out of this process is roughly this. Right? And that tells you that if your sterile neutrinos are at around a keV scale and the mixing is around 10 to the minus 9, then the relic abundance can be an order 1 fraction of what you see. And of course, this doesn't depend on them being at a keV scale because you can always tweak this mixing accordingly to accommodate pretty much any mass. But this is the abundance that comes out. And of course, they need to be stable over the lifetime of the universe, so you have to look at there are decay channels, and the decay channels are mostly three-body that go like this. So the mixing gives you connections to the active sector. So you go into 3 neutrinos for sure. If they're massive enough, they can also go into electrons and positrons, also go into mesons, and so whatever it can magically go into.
Is that what constrains this thing to be not much larger than KeV, or are you going to talk about what that constrains?
Yeah, so that is this together with constraints from X-ray data.
Okay.
And so the most visible thing that these sterile neutrinos give you is that they can go decay through this loop process into a photon plus an active neutrino. And so they're roughly masses compared to a sterile neutrino of a keV scale or heavier. And what you get is really a monochromatic photon line at half the sterile neutrino mass. And the decay rate goes as mixing times mass to the 5th power. So you can imagine that as I crank up my mass, it's going to decay even faster and faster. And so your X-ray strength is going to grow even stronger. And so this together with this constraint is what sort of picks the keV scale. So if you want this to be an order 1 fraction of dark matter, yet you want this to be not strong enough to violate observed constraints, then you get this following constraint. So the black line is where you get, the black line is where you get sort of the right relic abundance, and then these regions are all observational constraints mostly from XMM Newton of the Milky Way, Andromeda. So these are the most constraining ones, and they tell you that you are not allowed to live beyond this line, right? So roughly 2 keV is where the cutoff is. So if your sterile neutrino is heavier than a 2 keV, then you're running into trouble with observational constraints. And so that's a very solid.
Back one transparency here.
Mm-hmm.
Oh, I guess I'm not, still one more back.
Right.
Just trying to make sure I understand this formula here.
Uh-huh.
Okay.
Right. So you want to sort of hold sin squared theta times m sterile squared to be some constant number to give you the right relic density. Right? And then as you crank up your mass more and more, this goes up as the 5th power, and so they become more and more stronger. And so heavier guys will be more constrained, and this is what we see in this plot. And so that tells you that.
What are those dash curves?
So these dash curves are other production mechanisms that.
It's a lepton symmetry?
Yeah, so this is the lepton asymmetry, and so that's another way to produce it that I'll talk about in a couple of minutes. So if you do that, then there might be other ways to get around it. But purely this non-resonant production mechanism, you run into this wall at 2 keV, and then that's it.
Since the fact that all these experiments are bottoming out on this line, it's a line on this long line, is that because of some background that there's no way you're going to get
this?
around? Yeah, roughly all the experimental constraints,
Mhm.
right there. I'm wondering if there's some fundamental reason why that can't be pushed down.
They can. So it's just that the lifetime of this guy goes as the 5th power of mass. Right? So as they become lighter and lighter, the signals that they would give they just drop really fast.
Oh,
And so it's not a
well, I was
sensitive
thinking
issue.
of going down this way, so that's sine squared to theta.
Uh-huh. Oh,
But you're just saying the fact that it's that curve is just governed, yeah, because you're writing it as a function.
yeah.
Yeah, okay,
Yeah.
I understand.
Right.
Okay.
Yeah, right. So there you run it. So through this production mechanism, you run into this wall at around 2 keV, and so you want your sterile neutrinos to be lighter, but lighter dark matter particles are problematic because they are warm, right? So if they're light, they stream really fast, and so that will mess up with structure formation because they'll just run apart before structures can form, and so there are constraints on that too. So this Lyman alpha data measurements constrain precisely that. And they constrain the free streaming length to be roughly below, so this expression roughly needs to be below 0.11 megaparsecs. And so that is the constraint on, of course, the mass of the dark matter particle, but then it's also a constraint on what the average momentum of these particles is, and this, of course, depends on how you produce them. So people have looked at this in terms of sterile neutrinos, and they've found out that if you produce them through these oscillation channels, So this is called the Donaldson-Withrow mechanism. That's the most traditional way to produce them, right? Then the constraint is roughly order 10 keV. So this particular paper says that you cannot have a dark matter particle lighter than 28 keV. Otherwise, it's too warm to be out of dark matter. And so immediately, right, so you see this tension that the X-ray data needs it to be light, the free streaming data needs it to be heavy, and if you just take these numbers at face value, there's no parameter space left for sterile neutrino dark matter. Of course, that's assuming it is all of dark matter, right? So one thing you can imagine is that it's only a fraction of dark matter, and so this is a preliminary plot that we made that is, it's qualitatively correct, but not quantitatively correct. What the idea is that as your dark matter is heavier and heavier, your X-ray constraint gets stronger and stronger, and it tells you that it cannot be an order one fraction of dark matter. So it cannot be all of dark matter, but it can of course be a subdominant component of dark matter, right? So it can be, so it's going down 80%, 60%. So as your dark matter gets heavier, you can make a smaller fraction of dark matter, but of course you can still make dark matter. This other curve constrains it in the opposite direction, right? So as it's lighter and lighter, free streaming tells you that it cannot be all of dark matter, it can be a smaller and smaller fraction of dark matter, but as long as you live below these two lines, you're fine. Right? If you live below those two lines, then that means that you've satisfied both constraints. So for example, you could live there, and that means that if your dark matter is around 8 or 9 keV, it can be about 60% of dark matter, and it is okay with both constraints. And so these people have done a more careful analysis of this combined constraints, and they found that, for example, if your sterile neutrino is heavier than 5 keV, and if it's less than 60% of all of dark matter, then that's okay with both X-ray constraints and Lyman alpha. So that would be still a dark matter possibility.
Why is it so different? Okay, go ahead.
Uh-huh.
Go ahead. You said it wasn't complicated.
Yeah, so this is at the level of
Okay. Yeah.
digitizing plots from papers. Yeah, so that's one possibility, right? So you can have a sterile neutrino produced through the traditional Donaldson-Withrow mechanism be a fraction of dark matter. There are other alternatives as well. So as Yushin sort of pointed out, there's a different way of producing dark matter that is called the Shea-Fuller mechanism. And what it does is that if there is a lepton chemical potential present in the plasma in the early universe, you can have a resonantly amplified production of dark matter that resonantly amplifies production of certain momenta. And so you can pick numbers such that those momenta are colder than what the traditional production mechanism will give you. And so that means that your dark matter particles are now colder, and that means that you can get around the free streaming process and be consistent with both X-ray and free streaming data. And so this is something that works, and that's what these dotted lines are giving you. But then there's a fine-tuning involved, because to get the lepton asymmetry to be big enough in the early universe, you need to really tweak your parameters. And so it turns out to be a fine-tuning of about 10 to the 11. And so I will not really consider this as a viable scenario in this talk, but this is something that people, in particular the new MSM people, talk about all the time.
So what is the mechanism here again? I don't know.
So
Can
you just
easily
have a...
explain how chemical potential leads to resonantly amplified production?
So I've not looked into this picture in too much detail because I just sort of glossed over it as a
So
fine-tuned scenario.
change the neutrino oscillation phase. When you have some additional matter, it makes the oscillation more efficient. When you have more leptons, like a net lepton number in the universe.
So it's the effective mixing angle is different from this naive mixing angle.
So it's a resonant effect, sort of analogous to MSW.
Yeah.
Right.
Can I ask, in terms of when you say this tuning is required, do I understand right that what is required is an extremely large lepton asymmetry compared to, say, the baryon asymmetry, right? The equilibrium gives you a natural size for these
Yeah.
things, right?
So it's much bigger than what you need is much bigger than that.
And what is, when you say you get this fine tuning, what is even a way of getting it to be orders of magnitude larger? Like, what's an example? Forget about how tuned it is, just how do you even get that? Because it's an equilibrium type condition. You have to somehow be way out of equilibrium, right?
Yeah, so I've not
You
explored that
never, you
direction.
can never be in equilibrium. That's okay.
Yeah,
Anyway,
so,
I'm just curious,
yeah,
it
I haven't
sounds
looked
pretty
into this one,
bizarre.
but maybe you've looked into this.
Do you know how you can even get a huge lepton asymmetry? I don't care how
Oh.
tuned it is there, what's the basic idea? Because you can never be in equilibrium, right?
I think in this traditional Shifu, you need something else to.
You like
to
sphalerons will kill you. I mean, if you ever have sphalerons, they'll equilibrate the lepton and baryon.
Right. So definitely that needs to be below.
So it has to be
that.
generated at very low scale.
Yeah.
Right. You have some late decay of some particle.
I see. Okay. Well,
Yeah,
it sounds like it's pretty. Go ahead.
Yeah. You have to tune a lot of things.
Yeah.
Okay.
Okay.
So that's one way people get the right dopamine set. Another way that people have explored is just to extend the Higgs sector beyond the new MSM. So you add what is essentially a singlet scalar, call it S, right? If it couples to the sterile neutrinos like that, then once this gets a Vev, it gives you the traditional Majorana mass term. But what it also gets you is that it gets you a decay channel that goes S decays into two sterile neutrinos. Right? So if your S is something that is tied to the Higgs sector of the standard model, then you can imagine that the scalar is something that is in equilibrium in the early universe, and when it decays, you get some additional production of these sterile neutrinos, and they accumulate and they add up to be the dark matter that we see today.
So this S just decays way out of equilibrium, and it just decays to ends, and that's how you get your, directly gives your N relative abundance.
Mhm.
That's the idea.
Yeah.
How light does this S have to be?
So it can be at the electroweak scale, so hundreds of GeV. Or that's the number that these guys explore.
Okay.
So that's another way of getting these neutrinos out, but then that requires you to extend your minimal sterile or minimal neutrino sector, right? So you're adding another Higgs
But it's still
Sector.
renormalizable, so it function causes happy.
facts. Right. So I talked about three possible ways of producing it, right? And these are roughly the average momenta that correspond to these three processes. So Donaldson-Widrow, this ratio comes out to be around 1, and that turns out to be too big for the free streaming constraint. So remember, the free streaming constraint needed to be, this number needed to be below 0.11 megaparsec, right? So if it's about 1 and your sterile neutrino now is order 10 keV, then that's too big. But these other two ways of producing them, Schieffeler and this heavy scalar decay, are both fine with this constraint. And so that's how people potentially imagine producing sterile neutrinos to be out of dark matter.
Did they think about whether you could also get the baryon asymmetry from those same decays?
Both of the scalar?
Yeah, so you could get a, I guess if it's happening really late, depends on when it's happening, because, I mean, it gives a lepton asymmetry, which can turn into a
Right,
baryon.
you can turn it into a baryon.
But it depends, maybe if it's
It should
really
be
low
above.
energies.
Yeah, it needs to happen when the spheron is still active.
Yeah,
So,
so I'm wondering if it could work.
Um,
Because this other, I know that there's this other mechanism for baryogenesis, but it also requires some extremely special values, right? For the,
which one?
I thought.
For the oscillation of the
Yeah, the
tube.
oscillation thing
Yeah.
that you were talking about.
Yeah,
at the
so you
beginning,
need
right?
them to be
But
very
also, I'm not an
close to
expert, but that
degenerate.
requires some very special choices.
It does, yeah. So I think this mass spectrum needs to be EV scale for GeV scale guys.
Okay, well, anyway, I can look it up.
Yeah.
You don't know.
Yeah, so I don't know off the top. I guess they looked into that. But yeah, so this is how people imagine producing sterile neutrinos in the early universe. Right? And so this third mechanism in particular sounds interesting because in the setup that I mentioned earlier, right, there is a heavy scalar in the theory, the phi, that talks to the sterile neutrinos. And so you can imagine decaying that to give you some sterile neutrino dark matter.
Sorry, I'm sorry to keep going back.
Uh-huh.
Can we go back to this Kosenko Petrarchy thing?
one more back.
Well, I don't know. No, maybe this is. Well, anyway, I'm just wondering. Are these things cold enough? I mean, because if you're producing them from the decay of a heavy singlet, right?
Yeah.
Then it seems like they're not going to be particularly cold. I mean, they're going to be very
No, you expect them
relativistic,
to
and
be.
then maybe they can equilibrate or something. But
Well, but then, so
Remember that separate?
you have a redshift because of the expansion of the universe, right? So they're getting redshifted all the
Yeah.
time. And then there's additional entropy dilution. So those all factor in.
But they interact extremely weakly, so do they
Yeah.
really, I mean, so this has been, I'm just asking, I guess, this has been really looked at, like what is their,
It has, yeah.
what is their momentum energy distribution?
Mhm.
Okay.
Yeah, so they've worked that out, so you have to solve some
Okay.
evolution equation as the universe expands and
So
the number is
You're
big.
worried about if they're energetic, the cross-section will be too small?
They're
Well,
just
it's
gonna be
this
warm,
Higgs
right?
this singlet Higgs is decaying late,
Yes.
and then, but its mass is order 100 GeV.
Yeah.
Right.
So they're gonna be very energetic, these things, when they're produced.
Mhm.
So the question is, are they cold enough today, right? They have to cool somehow between the time when they were made and today, and I was just wondering if that's been looked at.
Yeah, but what would the cooling mechanism be, I guess, is the question.
Redshift is one, but, you know,
Mhm.
So when did they decay again? It's,
I mean, so you can,
well, I think,
look at what the lifetime, I think the decay is pretty prompt,
I
so
don't-
as soon as they
yeah, I
go.
don't
Oh,
think
it
they
counts,
have-
so it's,
because it's like a WIMP, right? I
Yeah.
mean, the 100
Right,
GeV
right, right.
Higgs is sort of like a WIMP,
Mhm.
so it's gonna have the right relic abundance, right? So roughly, it's a 100 GeV weakly interacting particle.
Mhm.
So if it's long-lived, it's just gonna dump all of its energy into the, so it probably can't decay it's not gonna be very long-lived, probably.
No, the
yeah,
decay
yeah,
is-
it should be
Right.
prompt.
Well,
prompt.
yeah, so it's actually,
Yeah, so as soon as it goes out of equilibrium.
so then it might not be able, that might answer my other question, it might not be out of equilibrium enough to give you enough baryons.
But people have also looked at cases where they're never in equilibrium. So you just produce these scalars through some
Yeah.
freezing mechanism, and so
Right.
they just sit there and then decay as they're produced. Right. So the number here comes out of all this. So the really meaningful number here is just as long as they're produced above the electroweak scale, this number is correct. And you need this because
Okay,
just
yeah,
counting the
that's
relative
true.
degrees of freedom, and them going down.
Okay, I'll let you go on.
Um, Yeah. So the claim is that it works. So we can try to get it to work with our heavy scalar too, right? We have a heavy scalar. We know it couples to the sterile neutrino. So let's just assume, just to entertain ourselves, that this is in equilibrium with the early thermal bath through some unspecified mechanism. So I won't tell you how it maintains equilibrium, but let's assume it does. Right? What can you get out of it? So one thing you get out immediately is that these operators will tell you that these annihilation processes occur in the early universe, right? So all of these come out of these operators, and they tell you that you have annihilation processes giving you sterile neutrinos in the early universe. Of course, this is suppressed by this heavy scale m star, right? But if the temperature is high enough, the center of mass energy will be high enough, and then that can help you overcome the suppression from m star. And so this can occur at some appreciable rate. And so if you roughly look at what the abundance coming out of this process is, it goes something like that, right? So there is some dependence on the mass of the guide you're producing. There's some dependence on the reheat temperature, because that's going to give you your energy scale for these processes, and it's suppressed by this heavy scale. But if the sterile guys are around a GeV scale, and this coupling X is order 1, and the reheating temperature is roughly close to m star, then you can imagine that this process contributes some non-trivial fraction of dark matter.
So this is a heavy sterile neutrino.
Yeah, so these are heavier. So these are really closer to a GeV scale. Yeah, so for a KeV scale sterile neutrino, this will not be, well, unless you crank TeV heat really high, so then it might work.
But what happened? Oh, so
Well,
it's a
just
small
this-
fraction,
this-
because you still have these X-ray constraints and all that other stuff.
Yeah,
And this is a small fraction, if it's over, at 10 GeV, it's a pretty small fraction.
not necessarily. So the X-ray constraint is coming out of the fact that these mix with the active sector, right? and that mixing was necessary because you're producing them through the Donaldson-Woodrow mechanism.
Oh,
Now you're
I'm
producing
sorry.
them through some other way. So the mixing might be 0, and then you'll get no X-rays. And this can be all of them. So there's this, right? There's also a different kind of freeze-in process where this, remember that the scalar gets a VEV. Once it gets a VEV, you also introduce decay channels, right? And so this heavy scalar can decay into 2 sterile neutrinos. The Higgs can also decay into a neutrino, active one and a sterile one. And so this happens with a dimensionless coupling that roughly goes as the scalar VEV to the M star, whatever your M star is. And so this can also contribute some fraction, and that fraction turns out to be roughly this. Right? So if your scalar VEV is order 1 factor within your scalar mass, then that tells you that if this coupling is roughly 10 to the minus 8, then you can get an order 1 contribution to your dark matter abundance through these decay processes. And remember that I want my phi to be around 100 PeV, which is 10 to the 8 GeV. M star is, say, the God scale, which is 10 to the 16, right? So this ratio comes out to be about 10 to the minus 8, and that's right in the ballpark that you need to get an order 1 fraction of dark matter. And so this can also contribute part of your dark matter abundance.
Okay, I forgot to ask, why is there no just NC phi linear?
So I've chosen my charge assignments so that NC and phi carry equal and opposite charges.
So you should be worried about NC5, kind of the direct mass, right?
Yeah,
Maybe
because,
build that with some R symmetry or something.
Yeah.
but anyway, it's just
So
an
that's one
assumption,
feature
it's
in
just
the-
an assumption, I gather. Is there any reason, I mean, does something actually go wrong if you chose the charge?
Oh, if you just chose something
you
that
had
gave you
a-
NC5.
Right,
So that would just mean that your NC mass scale will be whatever the phi VEV is, which is then PeV scale. And so this is just chosen with the motivation that you want your mass scale that goes into your theory to be some heavy scale, such as the PeV scale, yet your particle masses come out to be KeV to GeV scale. Yeah, so that's motivated just like that.
So why does your answer not depend on Y1? Why or why?
So here I've just chosen this to be the dominant process.
Oh,
And so for this one, you will get an analogous thing. Yeah. And so it turns out that Y's will generally be smaller than X's.
and here this sort of turns on at some temperature when you have
Yeah,
the
so
phase
once you-
transition,
right.
right? And so that
Mhm.
dependence has been put into the phi. You're sort of identifying those temperatures. I mean, that temperature
Into
indeed.
phi. Yeah.
Let's see, phi has a potential, right?
Uh-huh.
And so in principle,
Yeah, so there's some
dependence
order
on
one
the
correction.
details of the potential because of where the transition happens.
Yeah. Yeah, so this is the process that assumes that transition happened right at the beginning. But if you struck
Or
that.
is this IR dominated, so you don't even care? Is this Brownic abundance calculation dominated by the infrared, or is it dominated by the temperature?
No, so
where
this
the
it
transition
depends
happens?
on the high energy stuff. So this is something that gets accumulated when the phi is in equilibrium with the early path. So it's something that kicks in when the phi gets a VEV, and then it turns off as soon as the phi goes out of equilibrium.
Okay.
But then, so if you imagine that the time scale is proportional to 1 over t squared, right? That's how it goes. Then, yeah, it's going to be some order 1 correction to this expression. So it's 1 over t squared minus 1 over whatever the heavier turn-on time is.
So you say M5 is like PeV scale can be.
Yeah, so that's what you would imagine, right? So if the VEV and the mass are both around the same.
Can you get a PeV neutrino?
That'll show up in roughly 10 slides. Yeah.
Okay.
So you can also imagine scenarios where this guy is not in equilibrium, and you produce it gradually. As you produce it, it decays. But then I would need to write down an actual model to tell you what that number is. So I'm not going to worry about this additional production mechanism. But then this is also something that is in principle there. So let's just keep that in the back of our minds. So that was the lightest dark matter particle, but there are also two other heavier sterile neutrinos that are sitting around, right? And these actually give masses to your active neutrinos, so the mixing angle is very constrained. So mixing angle, so theta squared roughly goes as active mass over sterile mass. So once you've picked your sterile mass, sterile neutrino masses, you've picked the mixing angle with the active sector. So that's very constrained. And so once you constrain that, it turns out that the existence of these heavier sterile neutrinos that now decay into the active guys because of the mixing is very constrained by many recombination error observables. Right? So as soon as they decay into active neutrinos after BBN, you get into a lot of trouble with a lot of different things. So N effective might change, you might get distortions of the CMB, many things. So the best strategy is just to make sure that they decay before BBN, and then whatever they dump out just goes into the plasma, mixes with everything, and everything is fine. So generally, you would have these heavy guys decaying before BBN, which basically requires them to be heavier than a GeV. So let's remember that about these guys. You can also search for these guys directly, right? So it's not just the cosmology that constrains them. So if they mix a lot with the active guys, then you can actually try to produce them at direct searches and try to look for them. So the search roughly goes into two directions depending on whether you can see the sterile neutrinos directly or not. If they are invisible to your experiment, then all you can look for is sort of a peak difference, right? So say you produce a pion that decays into a lepton plus a neutrino. In addition to the neutrino, it can go into a sterile neutrino. And those two processes will give you different peaks for the lepton energy distribution. So you can hunt for this secondary peak. And depending on whether you find it or not, you can constrain the mixing parameter. So that's one way you can search for these guys. And you can also search for them through direct production and decay. So if they decay within your detector and they give you things that are visible, then you can constrain the mixing through that as well. And so you can imagine that this is going to be active at lower than the pion and K-meson mass scales. This is going to be more active as you go into heavier and heavier neutrinos because then they decay faster and faster. So putting everything together, this is what the parameter space for the sterile neutrinos looks like. The direct searches constrain roughly this area, right? So this is the peak hunt search that constrains hundreds of MeV scale sterile neutrinos. This is the direct searches for decay products that constrains closer to GeV scale sterile neutrinos, and they only constrain a large mixing, as you might imagine. Right, so the blue areas are ruled out, you can't live there. The red area is where they would decay after BBN but before the age of the universe, so they're not stable and they mess up observables. So the red area is not where you want your sterile neutrinos to live at either. There are searches for gamma rays that constrain this part of the parameter space. So this is assuming that the sterile neutrinos get produced through this Dawson-Widrow mechanism and they decay in the universe, and these instruments can look for those gamma rays. Right? And so that part is ruled out by these searches. And so what's left is roughly these two corners of parameter space that are interesting, right? Because I've colored them. So let's look at this part first. So this is where, so first of all, the green area is where you produce too much dark matter through oscillation. So this is also ruled out. The blue part is where you produce dark matter at a relic density that's between 1% and all of dark matter. So that sort of looks like an interesting ballpark to be looking at. And so this is all produced through Dawson-Widrow. You can see that this is sort of tens of keV scale, and there's going to be some additional constraint coming from the free streaming length constraint, but I've not put that in. But this is one area where you can imagine getting some amount of dark matter out of Dawson-Widrow. And here is a benchmark point.
Could you just go back a second? What about that corner up to the right? What are those little dots all about?
Oh, so the dots I'll explain later, but yeah, so this is all out, so you
That's
can have
allowed
sterile
too.
neutrinos there. So they just decay before BBN, so cosmology is fine, and they're not sensitive to direct searches. So that's a good point. So you can produce dark matter there, right? Here's a benchmark in our setup that produces that point. So you can see the scalar web is around 80 PeV. This is the Dirac mass matrix. So this is the couplings that we expect to be order 1, right? And you see that most of them are order 1, except this column. This is the sterile neutrino coupling to the scalar, and they're also order 1 except this guy, and this needs to be 10 to the minus 6 because, as Marcus pointed out a long time ago, the lightest guy needs to be keV scale to give you dark matter. The heavy guys need to be GeV scale to be okay with cosmology. So you have to have this 6 orders of magnitude hierarchy. And because of the 6 orders of magnitude, you also need the 6 orders of magnitude because if it's light, you don't want it to mix with your active guys. Otherwise, your masses are all screwed up. And your mixing angle is too big, so you suppress the mixing of this guy to the active sector. So what ends up is this active guy this lightest sterile guy will be at 8.5 keV. It will not talk to any of the active guys. These two heavier guys are at around the GeV scale, and they give you active masses to these two active guys. So the lightest active guy is essentially massless. The heavier two guys are at masses that give you the right oscillation data. And since this is Donaldson-Widrow, it gives you 1 dark matter, so it can only be a fraction of dark matter. Right? So this is 53% of all of dark matter. And so with these numbers, you get neutrino masses, and you get a sterile neutrino dark matter that's about half of dark matter. And numbers are all order 1 except for this number that's around 10 to the minus 6. Electron Yukawa, right? You think it's 10 to the minus 6, so maybe that's natural. But then that gives you, so these 3 sterile neutrinos are this red dot and then these 2 red dots. So those are where the 3 sterile neutrinos sit. So that was one corner of parameter space. There's this other corner of parameter space where the Friesen mechanism kicks in. So this is not dependent on the oscillation process, right? So this is where the scalar decays in the early universe and the dark matter density accumulates. And then in the blue region, again, between 1% and all of dark matter. And so you can see that the mixing angle is really tiny. Right? So I could have set it all the way to 0, and you would still produce them through decays of the heavy scalar. So this is not dependent on the mixing. And so this is the benchmark point that gives you these blue dots. So dark matter guy there, and then the 2 heavy guys up there again. Now you just need the mixing to be set to 0. The lightest active guy is accordingly 0. All the sterile masses are around the GeV scale. Couplings are all order 1. And so that's another corner of parameter space that works out nicely.
So let's see, the dark matter mass is just very, very small. Is that what I'm reading? Which is the main dark matter?
So this guy, so this is
Yeah, okay.
600 MeV. So then you can think about phenomenology, right? So I'll go through this quickly because I'm running out of time. So you have your dark matter guy, that's an order 1 fraction. It's a keV to GeV scale sterile neutrino that has some mixing. And you have some heavier steriles that I mentioned just earlier. So I won't talk about that again. And then you possibly have a BeV sector with definitely the scalar 5, but then additional particles sitting up at the BeV scale maybe.
Can you remind me why not much larger than the GeV? Why not larger than the GeV?
This guy, yeah. So that you can easily go up if you want. So it really depends on this number. Right. Yeah, so if you treat them in order for that to be an order 1 fraction dark matter, they can be much higher. Yeah. So if you want to live with a scalar web that's at PeV-ish scale, then they come out to be GeV. But they don't have to. So phenomenology, right? Of course, I have to mention this guy, right? So there's a 3.5 keV line, X-ray line, fits in perfectly with the sterile neutrino description. And so you can produce that in this model. There's been some issues about mismodeling of background, so the situation is unclear. But then one thing I would like to point out is if it's only a fraction of dark matter, a lot of these constraints are improved because issues like why you see them here in these clusters but not in dwarf galaxies or the center of the galaxy, you can tweak around because then different particles can be different contributions at different places, right? So the galactic center might be only 10% of these guys and 90% some other guy, whereas these galaxy clusters might be 50% these guys and 50% other guys. So there's an additional knob you can turn. And so this is slightly more attractive when it's a mixed state.
Can I just ask, is that quite the question of if you have a multi-component dark matter, how much the fraction of dark matter changes in different things? Has that actually been studied? Or is
That has been studied to some extent. It's still a very active area, research. But yeah, people have studied it to some extent, and I think they're still working. Yeah. And so the last thing I would like to mention is that you have the scalar and some maybe additional stuff at the PeV scale, right? And producing them directly is a challenge because they're all suppressed by this heavy steel M star. So your best bet of seeing them is maybe if they form an order 1 fraction of dark matter. So you can imagine a PeV scale guy that is some fraction of dark matter, and then you can hope that it decays into something that you see. And of course, there is something that is at the PeV scale that people have seen at IceCube, and this is actually something that is associated with neutrinos, right? So they see these 37 high energy events, TeV to 2 PeV scale, and people obviously wondered whether this was dark matter. And they tried to fit dark matter models to it, and they agreed that if it's something that decays with a lifetime of 10 to 28 seconds, it can be dark matter. So here's an example of a paper that does this. Dark matter spectrum is in green, background goes as red. Total is something that fits reasonably well to what IceCube is seeing, right? And since we have a naturally PeV scale theory, why not try to see if you can get this out of it? And so you can play this game, and it turns out that you really need the coupling to be suppressed. So 1 over M star suppression is just not good enough. So you need one more dimension in your operator. So you need a dimension 5 operator. So you can imagine this guy X has a charge of, say, minus 2/3 under the U1 prime. And then phi has a charge of +1. So this is the lowest dimension thing you can write down, right? And once phi gets a VEV, and X has a fermionic component that's lighter than the scalar guy, this scalar can decay into the phi plus 2 fermions. The 2 fermions doesn't matter what they do. The phi we know is tied to the neutrino sector. It decays into the sterile neutrinos. Those give you active neutrinos plus maybe other stuff, but you certainly have a lot of neutrinos coming out of the decay of this guy. And so you run the machine, you make the plot, and this is what the plot looks like. So we haven't put in all the efficiencies and dependencies in yet, but this is roughly what it looks like. Right? So the signal gives you the blue part, background gives you the red. When you add them all, you get something that looks okay by eye. So here is something that also pops out of this setup. So with that, just wrapping up. Right? So the aim was to tie this high-scale supersymmetry with the neutrino sector because this is a connection that's usually not explored. And we found that if you have a guy that gets a VEV at the PeV scale, and you add this U1 prime symmetry that gets broken by the VEV, then the active neutrino masses come out. There's a sterile neutrino dark matter that you can produce at mass KeV to GeV. If part of the dark matter also comes from the PeV scale, you can also get these IceCube neutrinos. And so there are many other directions that we're still looking at, but that's the story so far. Thanks.
There are more questions for Bibhushan? So I guess we have asked a lot of questions. So that's thanks and
I asked everybody else questions for them. So.
Yeah, thank you very much.
Very good. Okay, so let's thank Bibhushan again.